Okay, so today we will start a sequence alignment and edit distance topic. So we finished the last module on exact pattern matching in the last lecture. So far we have looked at the problems that involve exact pattern searching. For example, it could be either exact suffix prefix match or exact finding location of exact pattern match in a long text, or even longest common substring problem where we were looking for a common substring between two long strings. Now in that case we have looked at two scenarios where input was known at runtime. So there we looked at Z algorithm, and we have also looked at the index assisted algorithms, in which we looked at data structures such as suffix arrays, suffix trees, and Burrows-Wheeler indexes. For this lecture we are going to look at now approximate or inexact pattern matching. The key difference now will be that in the approximate pattern matching we will be allowing some differences in the matches. So for example, in this case, in this match occurring here, we are allowing some differences in the form of either substitutions, insertions, or deletions. So the matches that we will be interested in from here on will be considering small number of differences in those matches as well. So for these type of problems we will see several methods, and in most cases we will be using technique known as dynamic programming. So this module on sequence alignment will focus on exact approximate matching of biological sequences, and within that we will be looking at optimal solutions for solving those problems. In a later module we will come to the heuristics that will allow us to solve the same problems in a much faster time. So let us start this lecture with the simplest way of considering approximate pattern matching. So we will start with some basics of what approximate pattern matching means, why do we need it, what are the basic terminologies, and so on. So the key motivation for why we need approximate matching is that we have mutational processes acting on the genome. So we have already motivated this fact by saying that whenever we consider genome sequences of two individuals within the same species or sequences of different organisms, they will always carry mutations within them. So for example, in the bottom I am showing you CTCF protein sequence from 8 organisms: human, chimpanzee, wolf, cattle, mouse, rat, chicken, and zebrafish. And you can see that in their protein sequences you can find that although there are many characters matching within them, but there are also certain mutations that you can see within them, and the number of mutations can vary depending on the organism. So for example, the number of mutations between human and chimpanzee are fewer, versus if you think of human versus chicken or human versus zebrafish, there are many more mutations. So depending on how far the organisms are in the evolutionary tree, you can expect to see more number of mutations. So now when we are doing pattern matching of such sequences and we are comparing such sequences, naturally we have to allow some differences in the matches in order to see how these sequences compare to each other. Similarly, we can take one more example. Here we are considering mutations in SARS-CoV-2 data. So for example, if you compare SARS-CoV-2 genome sequence from Delta variant versus the reference sequence of SARS-CoV-2, here also you can see that there are certain mutations occurring in the protein sequences which necessitate approximate matching of these sequences. Similarly, the other reason for doing approximate matching is also the presence of errors in sequencing data. So for example, when we get sequences from any sequencing instrument which are raw sequences, they will always have certain rate of sequencing errors within them. And again, to process those sequences, we have to consider differences in those sequences during pattern matching. So, given this motivation, we will start the approximate matching module for these lectures, and let us start with some basic terminology. So, given the sequence alignment, right. So, we are in the pairwise sequence alignment, we will always be given two sequences as input. Let us call it sequence A, which is of length m, and let us consider the second sequence B, which is of length n. So, the first sequence has m characters from alphabet sigma, and the second sequence has n characters from alphabet sigma. In the sequence alignment problems, we are seeking to answer how similar are these two sequences. So, let us try to mathematically formulate this idea. So, consider two input sequences, again A and B. Recall the definition of a subsequence. So, a sequence X is said to be a subsequence of sequence Y if X can be obtained by deleting 0 or more characters from Y. So, for example, if my sequence is A, B, C, X, Y. So, if this is my sequence A, then B, A, C, X is a subsequence of sequence A, right. So, I can say that A, C, X is a subsequence of the longer sequence, because I can obtain A, C, X by deleting B and Y from the longer sequence. So, in this case I can say that A, C, X is a subsequence of A, B, C, X, Y, right. So, this is the definition of subsequence. Now, given this definition, we can formally define the notion of an alignment. So, the alignment between two sequences A and B is defined as pair of equal length subsequences U and L. So, an alignment, we are defining it as pair of equal length sequences U and L. So, U and L, both of them have H characters, let us say, because they are of equal length, both of them will have equal number of characters. Now, the properties of U and L are such that A is a subsequence of U, B is a subsequence of L, and U contains H minus M dash characters that are not present in sigma. So, I am considering a dash symbol which is not present in my original alphabet sigma, and similarly L contains H minus N dash symbols not present in alphabet sigma. So, an example is shown on the right, where you can see A and B sequences. A is, let us say, is triddle, B is a triple sequence. Then U, one example of how U and L can be built is I can define U as sequence of length 7. So, now observe that A is a subsequence of U, and U consists, in this example, U consists of one dash symbol, and the remaining symbols are from sequence A. Similarly, if you see the sequence L, B is a subsequence of sequence L, and it also has a single dash symbol. So, if you remove this dash symbol, then you get your sequence B back. In some sense, we are constructing these sequences U and L by inserting dash symbols in them, and these U and L sequences are of same length. So, we can sometimes think of them, we will also consider their column wise alignment. So, because they are of equal length, we can also construct them in a 2 cross H table. So, because you are two sequences and there are H symbols in both of them. So, I can think of it as a 2 cross H table as well. Okay. One caveat in this definition is that we will not allow U and L to have dash symbols in the same column. So, for example, I cannot have a situation where I build these sequences as riddle dash and triple dash, because in this case both a column has dash symbol on the same column. So, this is a restriction that we are imposing on the alignment. So, under this restriction this definition is what we will follow for defining an alignment between sequences A and B. Now, the motivation for why we are defining this alignment in this way will become clear in the next slides. Now, observe that if we take two sequences, let us say sequence A is ELV ELF and sequence B is let us say VIS Viz. Then observe that given our definition there are many ways of defining the alignment. So, for example, I can define my alignment like this, which has no dash characters. So, that is also an alignment because both sequences are of same length. So, here H equals 3 and you can see that A is a subsequence of U, B is a subsequence of L. So, that is a valid example. Similarly, this is also a valid example, this is also a valid example, all these are valid examples. And you can see that there are many ways in which I can insert these dash symbols and obtain a valid alignment. Now, given these many possible ways, it tells us that we need a method for quantifying how good alignment is, because the reason for defining this alignment is because we are seeking these approximate matches between two sequences, and for that we also need a way to quantify how good a alignment is. So, consider the following cost model. Again, let us say we have alignment of A and B defined as sequences U and L. Consider the unit cost model, that is, let us call a function C, which is the cost of defining any two characters from the alphabet sigma as well as including the dash character. So, in the unit cost model we will say that a character aligning to a dash symbol. So, if a character A belongs to sigma and the cost of aligning it to a dash symbol is equal to 1. Similarly, cost of aligning a dash symbol to a character from alphabet sigma is also 1. Cost of aligning two characters A and B, if they do not match, is 1, but if they do if the two characters match, then the cost is 0. That is, we are not penalizing at all if the two characters are equal, but in all other cases, that is when we are having mismatches or when we are aligning it to a character to a dash symbol, then we are penalizing a cost of 1. And now, considering this unit cost model, we can define the cost of alignment. So, given the alignment U and L, we can compute the alignment cost as considering individual columns of the alignment. So, for example, U1 comparing U1 to L1, U2 to L2, U3 to L3 and so on. So, we will add the cost and define the total cost for a particular alignment. Now, under this model, if you see the example on the right hand side, we can calculate C U comma L for this example. So, going by the unit cost model, we can say that this particular column will be have cost 1. Now, the next column is a match. So, this has 0 cost. The next column is a match, this has the 0 cost. The next column is a mismatch, so it has a cost 1. Again, in the next column we are aligning a character to a dash symbol, so it has a cost 1. and again the next two characters are matching. So, these both columns have cost 0. So, in this particular example the cost of this alignment is 3 because of the first column and the mismatch and the last third column. So, given this cost model we can give a cost to any alignment, and naturally now you can imagine what we will do next is, given all the candidate alignments we will seek an alignment which gives us the minimum cost, because that cost will reflect a good alignment between the two sequences, and that will give us how basically this will give us the sequences of this kind, because once we achieve alignment with minimum cost then we can look for how the two sequences are aligning together, and the equal homologous sequences will come together in single column and the differences will point towards mutations. Okay. So, given this alignment cost there is also one more way to interpret alignments. So, alignment AB can also be interpreted as a sequence of edit operations. So, for example, given this example on the right hand side where you see the sequence U and L, I can also interpret it as a sequence of edit operations. That is, when I say edit I mean character substitution or insertion or deletion, and these edit operations are being applied to sequence A so that it becomes equal to sequence B. So, for example, the first edit operation in this alignment is a insertion operation. So, I can say that I am adding symbol T at the first position of the sequence. So, here I am making an edit operation on the sequence riddle and I am adding symbol T at the first location. Now, another edit operation that I am doing here is substitution, that is there is a mismatch between D and P. So, that means I am substituting D to P. And finally, the third operation that I am doing here is I am deleting character D. So, if I see the D character here, I am going to delete this D character and I am going to remove it, and you can see that the finally what I am obtaining the string as triple, that is my sequence B. So, this is how using the edit operations I am converting sequence A to sequence B. I can also do this vice versa. So, this is symmetric in some sense, that if I start with B I can also apply these operations and get back A. So, this is a symmetric operation. So, in the unit cost model the number of edits. So, in the unit cost model the cost of this two alignments is 3, and in some sense because in unit cost model I am penalizing each edit by cost 1. So, therefore, if the cost is 3 it is equivalent to 3 edit operations in this sequence. So, now yes, so now in the assuming edit unit cost model alignment cost is 3 because we are penalizing each edit operation with cost 1. So, with this definition of alignment cost now we can frame a problem, right. So, now that we have the alignment cost defined and we know that there are many alignments possible between A and B, the problem formulation can ask for what is, give me in some way give me an alignment of A and B with minimum cost assuming unit cost model. So, mathematically I can write among all possible alignments of A and B, give me that alignment which achieves the minimum cost, and I am going to denote that minimum cost as D, capital D A comma B. So, the alignment that achieves the minimum cost I am going to denote the cost of that alignment as capital D A comma B, and this is again equivalent to minimizing the number of edits needed to convert A to B or B to A, right. So, because of the symmetry I can say it either way, and therefore, capital DAB, this notation can, this quantity can also be referred to as edit distance between sequences A and B, that is the minimum number of edit operations needed to convert A to B. So, I hope the problem statement is clear now, that is we are seeking an alignment that requires minimum number of edit operations to convert sequence A to sequence B. Now, we will follow the following strategy, that we will first compute the edit distance between A and B, and the second step will be that we will find an alignment that uses exactly DAB edit operations. So, as a first step, let us see how we can solve the edit distance between A and B. Now, our general strategy for this solving this problem, and even for some of the next methods that we will see, is that we will use dynamic programming technique. And as you may have seen in your fundamental algorithms courses, in this technique we are solving a given complex problem by breaking it down into sub problems using recursion. So, you have a big problem and we will solve it by breaking into sub problems using recursion. So, let me define the sub problem now. The sub problems I am going to define is in using the prefixes of sequences A and B. So, let me denote small dij as the edit distance between prefix of A that ends at I and prefix of B that ends at j, right. So, now I am solving the sub problem. So, I want to solve this sub problem and see whether solving this sub problem will help me solve the main problem, that is our main problem is to solve the edit distance between complete sequences A and B, and we will solve them using these sub problems. So, let us see how this is going to work out. First, let us look at some trivial scenarios. Well, what if I and j is 0, meaning that we are considering the edit distance between two empty strings. Well, that is going to be 0 because I do not need any edit operation to convert an empty string to another empty string. So, therefore, d 0 comma 0 is 0, that is trivial, I do not need any algorithm for solving that. Now, what about d I comma 0? Well, that means that the edit distance between prefix of sequence A and an empty string. So, this is the edit distance between prefix of A and empty string. So, in this case you can see that the minimum number of operations I need to do to convert prefix of A into an empty string is to delete all characters. There is no other way I can achieve an empty string. So, the minimum number of edit operations that I need to convert prefix of A into an empty string is I, because I will need to delete I characters of this prefix in order to obtain the empty string. So, this is I, and similarly you can argue that d 0 comma j is equal to j, because I will need to delete j characters from sequence B in order to get an empty string. So, these are all called base cases because these are all trivial, and we have defined I and j. So, we have defined this di comma j value for trivial scenarios where either I is 0 or j is 0. What about the natural case, which is d I comma j? How do we solve for this case? Because if we solve for this case, then we know how to solve our main problem. Our main problem is nothing but d m comma n, where m is the length of sequence A and n is the length of sequence B. So, if we know how to solve this, then we also know how to solve our eddy distance problem. Okay. So, for solving dij, I will make the following claim: the value of dij must be di comma j minus 1 plus 1 or di minus 1 j plus 1 or di minus 1 j minus 1 plus delta ij, where delta ij is defined based on whether the character ai is matching with bj. In that case delta is 0, otherwise it is 1. That is, these are the only 3 values that I need to consider. There are no other possibilities. So, in some sense this claim is saying that the value of dij must be one of these 3 values. There are no other there are no other possibilities. Now, why is that true? Well, to prove this claim, let us look at the alignment corresponding to eddy distance dij. So, if the eddy distance between prefix of A and prefix of B is dij, then we know that there must be some alignment that achieves dij edit operations. So, consider an alignment of ai a1 to I and b1 to j that requires dij edit operations, and consider all possible ways in which that last column of that alignment can look like. So, remember that alignment can be visualized as a table also, and let us focus on the last column of that alignment. What are all possible scenarios? Well, there are only 3 possible scenarios in which the last column can look like. The last column can either include ith character of A and jth character of B, or it can include ith character of A aligned to a dash symbol, or it can include dash symbol aligning to jth symbol of sequence B. There is no other possibility, because this is how our alignment definition is defined. Based on our alignment definition, the only way the last column can look like is one of these 3 possibilities in that alignment. Now, given that there are only these 3 possibilities, we can easily see that the value of di comma j must be either di minus 1 j minus 1, that is the best possible way in which you can align prefix of sequence A ending at I minus 1 to prefix of B ending at j minus 1, plus an additional edit operation that you may need for aligning ai to bj. So, that will depend on whether this is a match or a mismatch. If it is a match, then there is no edit operation needed, but if it is a mismatch, then there is a substitution operation needed. Similarly, in the second case, the alignment cost dij will equal the best possible way in which we can align the first I minus 1 characters of A to j characters of sequence B, that is di minus 1 comma j plus 1, because here we know for sure that we are requiring one edit operation, that is we will have to delete ai character from sequence B. Same way we can argue for the third scenario also, that is in this case the di comma j is equal to di j minus 1 plus 1, because we are again doing one edit operation, that is we are inserting character bj in sequence B. So, because the last column can only look like these 3 values, we know for sure in our claim that dij must be one of these values, there are no other possibilities. Now, there is one more simple claim I want to prove, that is the value of dij must be less than equal to minimum of these three quantities. And this argument is actually very simple, that remember that Dij is the minimum number of edits needed to convert prefix of A to prefix of B. So, it turns out that I can argue that there is a way in which I can convert A1 to I to B1 to J. I can convert sequence A1 to I to sequence B1 to J using exactly these many edit operations. There is a way to do that. So, how would I do that? Well, the way I would do it is, I would first convert sequence A1 to I into sequence 1 into sequence B1 to J minus 1 using exactly D I minus 1 I J minus 1 operations, and then subsequently I will insert Bj sequence at the end. So, I will insert this Bj character at the end, and you can see that this way I have a way to transform sequence A1 to I into sequence B1 to J using exactly D I J minus 1 plus 1 edit operations. Similarly, I can argue using the same logic that there is a way in which I can convert A1 to I to B1 to J using exactly D I minus 1 J plus 1 operations. So, because all these three are feasible ways to convert this sequence into sequence B, therefore, the minimum of these must also be feasible, right. So, because Dij captures the minimum number of edit operations, we know that Dij must be less than equal to minimum of these three possibilities, because Dij reflects the option of converting sequence A1 to I into sequence B1 to J with minimum number of edit operations. So, we have all these three options available to us, therefore, Dij must be less than equal to minimum of these three. Now, combining this claim and combining the previous claim, we know for sure that Dij will be minimum of D I j minus 1 plus 1, D I minus 1 j plus 1, and D I minus 1 j minus 1 plus delta I j. So, this is established using claims 1 and 2. So, now this gives us the recursion of how we can solve for D I comma j using its sub problems. So, as we traditionally do in dynamic programming, we have to think of a tabular way of computing Dijs, right. So, the way we will solve for Dijs is using by computing a table of size m cross n, right. So, in this case, on one dimension you can think of sequence A, on the top you can think of sequence B, right, and we will solve this table all the cells of this table one by one. The final value, that is D m comma n, will tell us the edit distance between these two sequences. The way we are going to solve for D I comma j, so suppose this is my cell I comma j, then observe that because based on this recursion, I comma j will depend on 3 neighboring cells. So, once I know the 3 neighboring cells, that is the upper cell, the upper left diagonal and the right cell. If I know these 3 values, then I immediately can compute this value as well using this recursion. So, given this kind of dependency in the table, the way we can solve this table is in a row format. So, that is we can compute first row, then using the values of first row we can compute second row. Similarly, using the values of second row we can compute third row and so on. We can also do this column by column, that's a choice that you can make, but we will have to solve it either column by column or row by row. So that when we are solving for I comma j, we have access to its above element, its upper diagonal and its left element. And once we have done that, once we have solved for the entire table, we will know the eddy distance between two sequences in the right bottom value. So, the right bottom value of this table will tell us the eddy distance between the two sequences. Okay. So, given this fact, we have achieved the first step of our algorithm, that is, we have solved for the eddy distance between sequences A and B, but now we also want a corresponding alignment, right, because the whole point of solving this eddy distance was to get a high quality alignment between sequences A and B. Now, we know that if the eddy distance is 2, the corresponding alignment will require 2 edit operations. But how do we compute that alignment? So, how do we compute the alignment corresponding to eddy distance 2 using the table that we have just computed? Well, that we can do using a traceback operation. So, what we can do is we can trace back our decisions when we were solving the eddy distance. So, for example, at this character I can check whether I computed my score based on the value above, or did I use the value on the diagonal, or did I use the value on the left. Depending on the choice I made, I can accordingly define my alignment. So, for example, in this case it looks like this score was computed based on its upper diagonal value, which means that in the recursion I would have used this particular way of achieving my score Dij. So, when I achieved score Dij, I must have used this value while solving for the minimum. So, this third category corresponds to a match or a mismatch operation. So, therefore, in this case I know that I have done a match operation, and therefore, I can align character C to character C. Similarly, I can keep going up and retrace what edit operations I am doing at each step. So, depending on the decisions I am making in my recursion, I can trace back the alignment operations that I am doing for aligning sequence A to sequence B. So, this is I will go all the way to the top left until we hit the corner, and along that we will trace the decision that we made in the dynamic programming, and those decisions will give us the corresponding alignment, right. So, as I said, there are 2 edit operations involved. So, you can see that the 2 edit operations involved are, one is here and the other edit operation involved is here. All other edit operations are, there are no other edit operations, all other decisions are made using match characters. So, along the diagonal there are matches happening, and anywhere where I am going sliding horizontally or vertically, those are corresponding to insertion or deletion operations. Now, in some cases there can be ambiguity as well when I am doing trace back. In some sense there can be more than one alignment which corresponds to the same edit distance. For example, when I am doing trace back, I am looking at what decision I am making between these 3, right, but it can happen that there are 2 equally good choices to make. So, for example, I can go either diagonal or left, both of them can be sometimes equally good, in which case I will have to make random decision. So, for example, if both of these suppose are giving me equal score, then I can make a random choice and I can take one of them, so that I have at least one trace back to reach the left corner. Now, in this trace back we will produce one alignment that corresponds to the eddy distance operations. In general, so for example, if you take this example where sequence A is principal and sequence B is principal defined differently, then observe that the eddy distance between these 2 sequences is 3. but there are multiple ways in which alignments are possible. For example, this is also a equally valid alignment which has 3 edits, and this is also a equally valid alignment which has 3 edits. So, in our traceback we will be reporting one of them depending on the choices we make. So, depending on the choice of diagonal up or left, you will be resulting in a one of these two alignments, which is okay, because all we want is one alignment that corresponds to the eddy distance. So, given this algorithm, now we have the eddy distance and we also have the corresponding alignment that uses minimum edit operations. How much time are we spending in this algorithm? Well, to compute the time and space, observe that for eddy distance we are solving a table of size m cross n, and each cell of that table requires constant time. So, each cell, because we are only considering 3 possibilities in the recursion, right. So, moving back in this recursion we are only considering 3 possibilities, that is up, left and diagonal. So, that is order 1 operation. So, each cell requires order 1 time to compute. Therefore, we are using order mn time and order mn space to solve for the eddy distance. Now, once we have that entire table, how much time are we spending to compute the traceback? That is, once we have the entire table, how much time are we spending to do this traceback? Well, as you can see, at each step we are going either left or we are going up. So, we are at least going one step left or at least we are going one step up, which means that the time to do traceback is order m plus n, right. So, that is we have to exhaust all columns and all rows to reach all the way to the top corner. So, eddy distance we are computing in quadratic time, that is order mn, and once our table is computed we are using order m plus n time to do the traceback and computing the final alignment. The question is, can we do better? Is order mn. So, if you look at the entire algorithm, this is order mn time algorithm now. Can we do better? Well, this question was open for a long time, whether there exists a faster algorithm for solving eddy distance or not. And one evidence was given very recently that it is very unlikely that a faster algorithm exists. So, this came from a theoretical computer science paper in which the authors proved that eddy distance cannot be computed in strongly subquadratic time. That is, if you are comparing sequences of length m, so if sequence A is of length m and sequence B is of length m, then there is no m raised to power 1.99 algorithm that can solve the eddy distance between A and B. And this is a conditional claim, because there is a holds under there is a hypothesis. So, this is a strongly exponential time hypothesis. So, unless this hypothesis is false, the authors proved that there is no subquadratic algorithm that can exist for the eddy distance problem. Now, about this hypothesis, so this is based on the popular problem of SAT problem in computer science. So, this hypothesis states that the SAT problem cannot be solved in 1.99 raised to power number of variables time. So, in SAT problem you have a bunch of variables, and we already have an algorithm which solves the SAT problem in 2 raised to power, that is a brute force algorithm. So, this algorithm is known, but a faster algorithm for this problem is not known, and the hypothesis states that the faster algorithm does not exist. Now, this hypothesis is widely considered to be true, but there is no formal proof for that. Now, under this hypothesis that there is no faster algorithm for SAT, if you make that assumption, then the authors were able to show that eddy distance cannot be solved in faster time. And in some way this gives a very strong mathematical reason for why faster algorithm for eddy distance may not exist at all. So, in some sense order Mn is the best we can try for solving this problem, and this is the simpler algorithm, simple dynamic programming algorithm that we have already seen. Okay, so I'll leave this lecture by giving you a food for thought, and in this case I want you to think about a special scenario where suppose the eddy distance between strings A and B is, let us say, k, which is very small, then both m and n. So, the eddy distance between these two sequences is extremely small than both m and n, that is to say that these two sequences are very identical to each other, their number of edits is very small. So, in this case can you come up with a faster algorithm that requires less time and space? So, I want to leave that thought to you, and you are welcome to think about alternate approaches of how we can optimize our algorithm to achieve a faster algorithm under this condition, and this faster algorithm can be in terms of k, m and n, but the faster algorithm should avoid quadratic runtime. So, it should be faster than quadratic. So, I will leave that for you to think, and in the next lecture we will look at more methods for approximate matching, we will look at more techniques as well. So, let us wait for the next lecture. Thank you.